Ever wonder how AI can decode not just words, but entire 3D worlds? Today, we're unpacking 3D Mo-Ray, a revolutionary model that bridges text, visuals, and spatial data in ways never before possible. Let's dive into its architecture, why it's a game changer, and how it's reshaping AI's ability to understand complex environments. The core challenge 3D Mo-Ray solves is merging three distinct data types: textual descriptions, 2D visual cues, and 3D spatial information. Think of it as training a machine to read a blueprint, visualize a room, and answer questions about its layout, all at once. How does it achieve this? Let's dissect its three-stage pipeline. First, the model translates each data modality into a unified numerical representation. For text, it leverages a transformer architecture, essentially a neural network that maps words into high-dimensional vectors, capturing semantic meaning. For 2D visuals, it processes 3D bounding boxes, think digital tags on objects, and projects them into the same vector space. But the real innovation lies in handling 3D scenes. Here, 3D Mo-Ray employs V-Otocap DETR++, a specialized module that analyzes point clouds, dense 3D scans of environments, and extracts spatial features like object positions, orientations, and relationships. This creates a language where text, 2D labels, and 3D geometry can interoperate. Now the magic happens, aligning these disparate representations. The model uses a three-step fusion process. First, it establishes cross-modal attention, like a translator ensuring text, 2D labels, and 3D points all reference the same objects. Second, it preserves contextual integrity. Imagine maintaining a story's plot while adding new details without contradiction. Finally, residual connections act as a safety net, ensuring critical information from each modality isn't lost during fusion. This is akin to a neural network's memory backup, reinforcing key features throughout the processing chain. Once fused, the combined representation feeds into a large language model, LLM, decoder. This is where 3D Mo-Ray shines. It doesn't just process data, it reasons with it. For example, if asked, "What color is the chair?" the model cross-references the text description, 2D visual labels, and 3D spatial data to pinpoint the answer. It's like giving AI a multisensory brain, capable of integrating sight, text, and space into a single, coherent understanding. Testing 3D Mo-Ray on benchmark datasets revealed stunning results. It outperformed existing models by 12–18% in tasks like 3D question answering and scene understanding. Notably, it excelled in zero-shot scenarios, answering questions about objects it hadn't explicitly seen during training. This suggests the model isn't just memorizing data, but genuinely grasping spatial and semantic relationships. This work isn't just a technical achievement, it's a paradigm shift. By unifying text, vision, and 3D reasoning, 3D Mo-Ray paves the way for AI systems that can navigate virtual environments, assist in architectural design, or even enhance augmented reality. But behind every breakthrough lies a network of collaboration. Funded by the National Key Research and Development Program of China, the Beijing Natural Science Foundation, and the National Natural Science Foundation, this research builds on decades of work in 3D scene understanding, transformer architectures, and multimodal learning. 3D Mo-Ray isn't just a model, it's a glimpse into AI's future. By merging modalities, it's creating systems that don't just process data, but comprehend it. As researchers continue refining these techniques, we're one step closer to machines that see, read, and reason like humans. Thanks for watching, stay curious, and keep exploring the frontier of AI.